Okay, so next up here in Module 3e, we're going to take a look at what are called discrete random variables. A discrete random variable, well, first we need to talk about what a random variable is, generally speaking, and then we'll define what a discrete random variable is. Along the way, we're going to introduce the idea of expected value and standard deviation for a discrete random variable. Expected value is an alternate terminology for what we've been calling the mean. We're also going to take a look at something called the population average treatment effect, or PATE, and the concept of balance. All right, so in any probability distribution, any random variable, you have a set of all possible outcomes that might occur. If we have the simple case of flipping two coins and each coin has a head and a tail, then the sample space is going to consist of these four combinations, or permutations, I should say. Head-head, head-tail, tail-head, or tail-tail. Now, I haven't said anything about whether these coins are fair or not. It's not necessarily the case that the probabilities of each of these outcomes is the same. But if the two coins are fair, then the probability of each of these possible outcomes is the same. A random variable, sorry, a little too much highlighting there. A random variable is some kind of random event to which we're going to assign a numerical value. And for most kinds of measurements, we just get a numerical value automatically. We don't really think about it. If we're measuring height or weight or temperature or age or distance, all of those things are inherently numerical. But some things are not numerical, and in order to treat those as random variables, to be able to do things like computing means and standard deviations and probabilities and so on, we have to make an assignment of some numerical value. For example, if we're thinking about a coin where we've got a head or a tail as the possible values, what is an average coin flip? Well, the only two possible coin flips are head or tail. What is an average coin flip? Well, what the heck do you mean? We have to assign some kind of value to each of those outcomes, some kind of numerical value. We might assign a value of 1 to the head and 0 to the tail, and then we could say, okay, the random value is this assigned number. So if I flip the coin once, I'm going to get a value of either 1 if I got a head or 0 if I got a tail. If I flip a coin twice and I count the total number of heads that I got, I might have 0 heads or 1 head or 2 heads and so on. All right, so if we assign the number of heads that we flip, then in the case of 2 coins, the random variable's value will have a 2 if we get 2 heads, a 1 if we get a head or a tail. Notice in this case that the ordering of the head and the tail doesn't matter in this assignment, in this specification, and we get a 0 if we get both tails. So in this case, the random variable, which counts the number of heads for coin flips, 2 occurs 1 time out of 4. 1 occurs 2 times out of 4, and 0 occurs 1 time out of 4, assuming that these are fair coins. Random variables, which are these variables that have numbers assigned to them, are either discrete or continuous. The distinction is that a discrete variable is a variable that has some countable number of values. That is, we can assign some integer to each possible value. It is possible for a discrete variable to have an infinite number of values as long as that's a countable infinite number. Now, in the case of coin flips, it's kind of obvious that you're going to get either a head or a tail. In the case of a die roll, it's kind of obvious that you're going to get a 1, 2, 3, 4, 5, or 6 if you have a fair six-sided die. Other things are less obvious, like if I have a cup of water and I ask you how much water do I have, well, you could argue that, you could say, well, you have 1 cup of water. Surely that's a continuous variable. Surely that can't be counted. But actually, technically, I mean, it wouldn't be easy to do, and I'm not sure how accurate you would be. You know, water is composed of water molecules, so you could, technically speaking, count the number of water molecules that exist within that cup of water. If you have a discrete random variable for which you do have some huge number of possible variables, it's often the case that you treat that as a continuous variable anyway, just for mathematical simplicity. I gave examples like height, weight, time, distances, and so on. As another example, if you're doing finance, you're keeping track of money, the prices of things, and also returns on things. Now, if you're trading stocks on one of the U.S. exchanges, the stock prices are quoted to the penny. And so technically these prices are discrete. You might pay $50.01 for a stock, or $50.02 for a stock, or $50.03 for a stock, but you can't buy an individual share of a stock for $50.01 of a cent. Okay, so technically speaking, prices on stocks are discrete, but you know, there are so many possible prices that to make the mathematics easier to handle, we treat that kind of thing as continuous. All right. Now, to describe the probability of each of the possible outcomes in a discrete distribution, we define something called a probability mass function. The probability mass function assigns an individual probability to each of the possible values of the variable. There are 2 constraints on this. First of all, the probability of any outcome has to be greater than or equal to 0. We can't talk about negative probabilities for any outcome. Also, if we sum over all of the possible outcomes, the sum of the probabilities of all of the possible outcomes has to be 1. Okay? That is, when we do an experiment, when we do a trial, when we make an observation, something has to happen. And so the probabilities of all of the possible outcomes, those have to sum to 1. Here we have a fancy diagram of a dish containing some marbles or balls. And let's suppose that we've got these things labeled with numbers so that we can treat these as random variables. If we look at this, we've got 0. We've got 1 occurrence of a ball labeled 0 out of a total of 10 balls. We have 2 3s, 3 1s, and 4 2s. Okay? So we can describe the probability mass function for this collection of labeled balls, basically by just creating a table, we can say that the probability of drawing the 0 is 1 out of 10. The probability of drawing a 1 is 3 out of 10. The probability of drawing a 2 is 4 out of 10. And finally, the probability of 3 is 2 out of 10. If we add these things all up, they sum to 1.0, and each of these probabilities is greater than or equal to 0. So this is both a reasonable and a correct probability mass function for this scenario. The mean, also called the expected value of a random variable, is simply the sum of the value of each the value of each possible outcome times the probability that that outcome occurs. All right, so the mean value for these 10 balls is, well, we might draw the ball labeled 0, and the probability of that occurring, as we've seen, is 0.1. So we might get a value of 0 0.1 of the time. We might get a value of 1 0.3 of the time, or 2 0.4 of the time, or 3.2 of the time. And if we just do this computation and add everything up, we conclude that the mean ball value is 1.7, or the expected ball value is 1.7. Now, I'm sure I've mentioned before, but I just want to mention again that notice that 1.7 is not a possible ball value. The only possible ball values are 0, 1, 2, and 3. But we just define the mean, or the so-called expected value, using this computation. Once we've got the mean, we can use that to compute the variance of this situation. And the variance is defined as the sum over each of the possible outcomes of that outcome's value minus the mean squared times the probability of that outcome occurring. All right, so we have computed that the mean value of a ball drawn from this bowl is 1.7, and we can now compute each possible value minus the mean squared times its probability. And if we do that, I won't, you can read that. What we get is that the variance of this scenario, the variance of these balls in this jar, is 0.81. And the standard deviation is simply the square root of the variance, which is 0.9. Now, you might be wanting to complain that, hey, wait a minute, aren't we supposed to be dividing by n minus 1 somewhere in this equation? The answer is no, we're not dividing by n minus 1 here, because this is the entire population of balls in this bowl, okay? So we are computing the actual population variance and standard deviation of all of the balls that are contained within this bowl. All right, so let's try another example here just to test understanding of these concepts and equations. First of all, we're asked to calculate the expected value of x. So x here is going to be the number of heads that appear when we toss 3 coins. We've got a fair coin. We're going to flip it 3 times. we can enumerate the possible outcomes. Okay? There have to be 8. There are 2 possible outcomes for each coin flip, and we're doing 3 coin flips, so there have to be 2 cubed outcomes possible. And they are going to be head, 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 tail, head, tail, head, head, tail, tail, and then tail, head, head, tail, head, tail, 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 head, and tail, tail, tail. All right, so those are our 8 possible outcomes. Now, if for each of these possible outcomes we count up the number of heads that there are, we get 3 as the value in that case, 2 as the values of these 3 cases, 1 as the values of these 3 cases, and 0 is the value of that case. Now, each of these possible outcomes is equally likely to occur. Consequently, our expected value of x is going to be the sum of the value of x times the probability that we got that value, and that's going to be 0 times, well, 1 out of 8. We have 1 out of 8 ways of getting a 0, so that's 0 times 1/8, 1 times 3/8, 2 times 3/8, and 3 times 1/8. All right? Okay, so we've got 3/8 plus 3/8 plus 6/8. 3 plus 3, that's 12/8. 12/8 is 1.5. So that's going to be 1.5. So on average, we would expect to get 1.5 heads when we flip a coin 3 times. And intuitively, that just makes sense, right? Intuitively, if we're going to flip a coin 3 times, we would expect half the time to get a head, and so that would be 1.5 heads on average. Next, we're asked to calculate the variance, and we can do that manually as well. So let's compute the variance of x. Okay, that's going to be the sum of x minus mu squared times the probability of x. Alrighty, and so 0 minus 1.5 squared times 1/8. Okay, I'm going to decline. I'm going to decline to write this out by hand. Well, let me write out a couple of terms. So this is going to be okay, so this is going to be 0 minus 1.5 squared times 1/8 plus 1 minus 1.5 squared times 3/8, blah, blah, blah. All right, I'm going to just compute that in my big Excel spreadsheet and show you what that result is. Let me pull that up. Okay, so this is going to be 0 minus 1.5 squared times 1/8 plus 1 minus 1.5 squared times 3/8 plus 2 minus 1.5 squared times 3/8 plus 3 minus 1.5 squared times 1/8. And it is. Forgot to put my equal sign in here, so let me put my equal sign in here. And it is 0.75. Okay, it's being displayed in exponential notation here, but it's 0.75. So this turns out to be 0.75. And then the standard deviation is the square root of 0.75, which is going to be greater than 8, less than 9. It's going to be somewhere around, I don't know, 0.86 or something. Not sure exactly. Now, did you notice that this is discrete random variable follows a binomial distribution? We're simply counting the number of successes, the number of heads. So let us apply the formulas that we talked about in the previous module that should give us the same answers as what we got here by cranking it out manually. All right? You may or may not remember from the last module that the mean is simply the number of trials times the probability of success. The standard deviation, the variance is the number of trials times the probability of success times the probability of failure. And the standard deviation is simply the square root of that. NPQ. All right, so this is just going to be, we're doing 3 flips, and the probability of getting ahead is 0.5, so that's 1.5, which is what we got. And this here is 3 flips times 0.5 times 0.5, which is 1.5 times 0.5, which is 0.75. Amazing, amazing. So the formulas give us the same result. And here we take the square root. I did throw this into a calculator. It is about 0.866 and something. All right, so if you remember the formulas, it's a lot easier to use the formulas if you recognize that this is a binomial distribution. Otherwise, you can use the definitions of expected value and variance from the computations and get the same result. Okay, so next up we're going to take a look at what's called the population average treatment effect, or PATE. This is not something like the mean or the variance that there's any theoretical foundation for based on the distribution. This is something that we estimate from data collected in an experiment. And let's set this up by defining some terms. Let's have y represent some outcome of interest, which, as an example, let's suppose is calories consumed in our fast food restaurant experiment. Let's call t the treatment given to participants in this experiment. And in this particular case, the treatment given to each participant will be that they received calorie information. Now, not everybody received calorie information. Calorie information was given to people at random, and we'll call the control group, which is everybody who did not receive calorie information, TC. Now, I hope it's clear that T, the people who did receive the treatment, and TC, the people who did not receive the treatment, that those are mutually exclusive and exhaustive sets. T plus TC is the entirety of everybody who participated in the study, and each person was either in T or in TC, but it's not possible to be in both. So the population average treatment effect is the probability, I'm sorry, not the probability, the expected value of the outcome, that is in this case the expected value of the calories consumed, given treatment, that is, this is the calories consumed for the experimental group, minus the expected value of the calories consumed not given the treatment, the control group. So was there any increase or decrease in the expected value of calories consumed in the test group versus the control group? Okay. Now, because these sets are people who did receive treatment or people who did not receive treatment, these are referred to as counterfactual groups or counterfactual worlds. If we can imagine a world of people who didn't receive treatment versus a world of people who did receive treatment, and our samples are representative of those worlds. Okay, so we can fill in this thing called a contingency matrix showing the average amount of consumption for the control group, the people who did not receive treatment, versus the people who did receive treatment. And this is going to depend on something that we didn't bother to mention in the actual experiments called the motivation level. And let me describe what this means. People in the low motivation group are not inclined to pay any attention one way or the other to our calorie information. These people have low motivation to change their calorie consumption behavior. Then we have a group of people who have high motivation. These are people who are highly motivated to improve their health, their calorie consumption, whatever. And then we have this third group called the adverse group. And these are people who don't like to be bothered by experts. All right. So these are people who, if they are given calorie information, may be, rebellious and actually consume more than they might otherwise consume. And we're just assigning arbitrary probabilities to people here being in the low motivation or high motivation or adverse motivation groups. Okay, this is not part of our study. But in the control group, let's suppose that the people who are not very motivated about their health consumed on average 850 calories. The people who were motivated about their health consumed on average 790 calories. And the people who are adverse to being bothered by experts consumed 800, which is pretty close to what the highly motivated group consumed for whatever reason. We just observe these numbers. Now, in this alternate universe, this other group where we did give people calorie information, the unmotivated people had no change in their behavior. They ate the same amount of calories on average that they did before. The highly motivated group ate fewer calories on average. The adverse group, having been annoyed by this person handing them something to read, actually ate more. Okay, they actually increased the amount of calories that they consumed, and this is real. This is this is human behavior that you have to take account of. For example, very recently and unfortunately, the COVID vaccine. There were people who were not particularly motivated one way or the other about the vaccine. There were people who were strongly motivated to get the vaccine when they learned that the vaccine was very effective. And there were, unfortunately, people who were even more determined not to take the vaccine when some experts told them that they should. Okay, so, this kind of stuff matters. All right, so if we assume that these probabilities here make some sense, that we've got 0.3 with low motivation, 0.5 with high motivation, and 0.2 adversely motivated, then the expected value of the consumption of calories given calorie information computes out to 760 calories. The expected value of calories consumption given that people were left alone and not provided with calorie information, the control group, computes out to 810 calories on average. And so by our definition of the population average treatment effect, we can compute the expected value of consumption given treatment minus the expected value of consumption not given treatment is minus 50. Is a negative number bad? No. In this case, we are hoping that our treatment is going to cause people to eat fewer calories. And so this is a piece of information that they did eat fewer calories. All right. Now, so that's what the PATE is. It is just an average. Okay, it doesn't apply on an individual basis. In fact, this is maybe a little bit of an extreme statement that it applies to no one, but these numbers are all averages. The PATE itself is an average. So given that we've got, 600, 650 people in our study, it's very unlikely that, any one individual experienced exactly this treatment effect. Another problem here, it has to do with this adverse group. Sometimes providing a treatment can actually backfire. That is, you provide a treatment, you tell people that the treatment is good for them, but some people get annoyed by that or indignant about that and avoid the treatment. And in that case, it's possible that unless the treatment is extremely effective, you may actually end up doing net harm by offering the treatment. Okay. Blah, blah, blah. Okay, this other stuff I'll just let you read. Anyway, so you may encounter this idea of PATE, the population average treatment effect in your life. Now, another thing that we were very careful about in the study is to do randomized treatments in order to achieve balance or, zero effect based on all the other factors that were not things that we were studying. And in our study, we measured a whole bunch of so-called demographic things that we were not expecting to change. We asked people their hunger level, their height, their weight. We computed BMI, body mass index values, and kept track of all of this stuff. And we want to discover, and we do discover this by analyzing the data after the study, that the treatment group versus the control group, that there's no particular difference in hunger levels, no particular difference in BMIs, no particular difference in heights, no particular difference in weights, et cetera, et cetera. So we do have balance in our groups across the things that we were not attempting to modify. Okay. All right. Well, I'm going to just let you read this other stuff here. One other question here, though. Suppose in the fast food experiment, everybody had been given an option as to whether they wanted to receive calorie information, as opposed to, at random, some people being given the information and other people not being given the information. Would this have any impact on the population average treatment effect? Well, yes. Now you have what's called self-selection going on in the test population, and it's likely, remember that we have these different people with these different levels of motivation. It's likely that everybody who is highly motivated is going to ask for the information. People who are adversely motivated are definitely going to not want the information and may still eat more, even after having not taken the information. And there's probably going to be no effect on this unmotivated group. So this is going to end up exaggerating the apparent treatment effect by the people who are highly motivated self-selecting and saying, "Oh yes, I want the calorie information." So it will appear as though the treatment effect was even better than it actually would have been in a randomized experiment. Okay. All right, well, let's take a look at this test of understanding question here. And this is similar to one that we've done before, but now we know more about how to compute expected values and variances. You have an opportunity to flip a coin 10 times. If you get 3 or fewer heads, you lose $10,000. If you get 4 to 6 heads, you win $10,000. And if you get 7 or more heads, you win $20,000. What is the expected value of this gamble. All right, well, let's have a look. Let me pull up my... here's my document camera, and now let's take a look at how we're going to do this. So, we know that the expected payoff, I'm just going to call it payoff, is equal to the sum over the possible payoffs of payoff sub I times the probability that we receive payoff sub I. And there are three possible payoffs here, which are minus $10,000 times the probability of X, the number of successes, the number of heads, being less than or equal to 3, plus $10,000 times the probability that 4 is less than or equal to X, which is less than or equal to 6, plus $20,000 times the probability that X is greater than or equal to 7. All right, so that's the computation that we need to do. Now, remember that the number of heads that we get out of these 10 trials, this is a binomial variable, so we're going to use our binomial widget to compute these probabilities here, and then we can combine that with these payoffs to compute the expected value. All right, so let me switch to my here's my binomial distribution device widget, and the number of trials that we're doing is 10. The probability of success, the probability of getting ahead, is 0.5. We want, for our first thing, to compute the probability of having less than or equal to 3 heads. Okay, and we are told that that probability is 0.1719. 0.1719. Then we have the probability that X is between 4 and 6. So let us choose this widget instead. 10 trials, probability of a head is 0.5. The lower bound is going to be 4, and the upper bound is going to be 6. All right, so the probability that X is greater than or equal to 4 and less than or equal to 6 is 0.6563. 0.6563. Okay, so that's the second probability. And then, well, one way we could compute the third probability is to just compute 1 minus each of these two, but I'm too lazy to do that, so let's go ahead and ask let's ask our widget to do it. And so this is going to be the probability that X, well, probability of X being greater than or equal to 7 is the same as the probability of X being greater than 6. And so that's also, unsurprisingly, 0.1719. Okay? This binomial distribution is symmetrical, And so the probability of getting a zero, of getting, well, there is a tiny probability of getting zero heads. It's very small. The probability of getting 0, 1, 2, or 3 heads is the same as the probability of getting 7, 8, 9, or 10 heads. And I guess for the 10 here, you can see that there is a tiny little smudge of orange indicating that there is some really tiny probability there. In fact, let's ask, what is the probability? 6, 7, 8, 9. All right, so the probability of getting more than 9 is 0.001, according to the tool here. I'm guessing it's probably actually less than that. That's probably just the lowest value that this thing is willing to display. All right, so we have our probabilities, and we can now actually do this computation. Once again, I'm going to pull up my giant spreadsheet for this purpose. We'll get rid of this computation we have from before, and we're going to compute minus 10,000 times 0.1719 plus 10,000 times 0.6563 plus 20,000 times 0.1719. And our answer is $8,280. All right, so that is our expected payoff. The question becomes then, would you take this gamble? And the answer is similar to what we talked about before, which is whether you take this gamble or not depends on how risk-averse you are. If the concept of losing $10,000 is so painful to you that you're not is more painful to you than the likelihood of winning $10,000 or $10,000 or $20,000, you would probably decline this gamble. But if you could do this as many times as you want to, that is, suppose that this offer was made to you saying, well, all right, look, we're going to play this game, and we'll settle up when you're done playing. All right, so you get to decide that you play this game over and over and over and over and over and over and over again, and we'll settle up after all of the times that we've done this gamble. Well, in this case, absolutely, you would on average over a long period of time gain almost $8,300 on average each time you play this game. It is microscopically possible to lose money after playing this game for some large number of times. But the more times you play it, the tinier and tinier and tinier that probability becomes that you might actually lose money. And so yes, you should definitely take this deal if you're allowed to do this as many times as you want. Okay, well, that is that.